Hello, everyone. In this lesson, I wish to go over some questions from homework on how to decide the domain of a function. We're going to be using this quite a lot. So let's take a look. Okay, we have all these contents I would like you guys to study and review. And one of those sections is review functions. Okay, this is an hour long lesson. And yeah, please study this section. Of course, we also have other content. So let's go straight to domain of a function. After we study the basic functions, right, those functions in the most basic form, then from that knowledge, we can decide domains for all of these functions, okay? As you can see, when these are variations of basic functions. For example, the first one, okay, so let me type it. F of x is equals to x plus 1 and over x minus 5. This function has a numerator and denominator. If you look at the numerator is a polynomial. So its domain is all real numbers. The denominator is also a polynomial. So this is a rational function. So for a rational function, which we have numerator whose domain is all real numbers, the only part we need to work with is to guarantee the denominator is not a zero. So there are two ways to set up, okay? So generally two major steps. The first step is setup, okay? So when we set up, you just make sure that the denominator is not zero. So for this question, when I set up, I would just put the whole of the denominator not equals to zero. Okay, and then we solve this inequality. So the second part we solve. We don't have to make it so clear, set up and solve, but in your mind, you know there are these two steps. So as a result of solving this inequality, we get x not equals to 5. So that's the domain, okay? So when then you say the domain is x is not equals to 5. How do we read that? It's read as the domain of the set function is all real numbers except 5. So when you write it like this, it's perfect, okay? Another way to do this, okay, some of you might have seen other teachers doing, instead of setting up as x minus 5 not equals to 0, and we set, and it's been set as equal to 0. The underlying statement by doing this is to say, I'm going to find out what are the numbers cause the denominator equals to 0. And I'm going to find those numbers and exclude those numbers from the domain. So of course, if you solve it, you're going to get x equals to 5. But your domain is still the same because it's the difference is in setting up. If you set up not equals to 0, then you get x is not equals 5, that's your domain. If you set it up as equal to 0, then you know the denominator cannot be 0. So the opposite of equals to 5 is not equals to 5. So there's a logically opposite way to setting this up. All right, so I hope you understand. Either way you set up, you need to be very clear about what you're doing logically. All right, so let's look at the second question. Okay, the second question is g of x. G of x equals to cubic root 3, a cubic root x over, I believe that's x squared plus 1. Okay, I think it's x squared plus 1, so let me double check. Oh, I should wear my glasses. X squared plus 1. All right. Okay. So in this case, actually, you will notice that the numerator has a domain of all real numbers. The denominator is x squared plus 1. And we can do what we just did by setting up x squared plus 1. But you may also notice that since x squared is always at least 0, right? As a result, x squared plus 1 will not be 0 for any real number. As a result, the domain is just all real numbers. The domain is all real numbers. So this is the case. You can either reply the domain is all real numbers, or if you say I need to provide some reason, and these are the reasons you can provide. All right. And let's look at number 3. Number 3, we have f of x equals to, right? We have a rational function once again. So x minus 2 in the denominator. So once again, we have a polynomial in the numerator, we have a polynomial in the denominator. And so we should set up the denominator not equals to 0. Then you say, hey, wait a minute. I can factor the numerator, right? I can factor the numerator. If you factor the numerator, you're going to get x minus 2 multiply x minus 3 divided by x minus 2 and say, hey, I can cancel x minus 2 and I'm going to get x minus 3. Can I do that to determine the domain? Well, the answer is no. The answer is no. Why? Because remember our mathematical principle. Okay, our mathematical principle says anything times 1 stay the same. Okay, anything times 1 stay the same. Excuse me. So in this process, when we cancel x minus 2, x minus 2, we're really doing x minus 2 divided by x minus 2, right? And x minus 3. So we can put the x minus 3 on the side. Okay, so however way you prefer to put it, and I just, you don't have to write this step. I'm just making a point. You say, hey, this is 1. Well, this is only 1 if x minus 2 is not 0. Okay, so you can only cancel. Okay, so this step. Okay, so I'm going to put a little arrow here. So this step to make it 1 can only be done if x minus 2 is not 0. Then you say, what if x minus 2 is 0? Then you can't do it. You cannot do it. Because if x minus 2 over x minus 2, x minus 2 is 0, a 0 over 0 is undefined. In mathematical principle, we can only make one when numerator is the same as the denominator, only when no 0 divided by 0 involved. Okay? So understanding this, you would not say the domain is all real numbers. No, the domain is x is not equals to 2. X is not equals to 2. X is not equals to 2. So from that perspective, is this reduction necessary? The answer is no. The reduction actually is not necessary. So let me give you another version of determining the domain for this function. Okay, I'm going to determine the domain. I'm not going to do any reduction, because even if you do the reduction, you still have to pay attention to the making of one, right? Mathematical principles apply here. Therefore, all you have to do is just to set up, right? X minus 2 is not 0, right? Just put it here. And as a result, you solve. Then you get x not equals to 2. And you're done. That's the domain. So that domain is done. So then you say domain is x is not equals to, meaning the domain is all real numbers except 2. Then you say, what if I reduced it, right? If you reduced it, it's not a crime. It's not a crime, okay? If you have reduced it, okay, so I'm going to give you another version. If you have reduced it and you get that, and then you tell the teacher that the domain is all real numbers, this is the case that you are wrong, because the reduction cannot be done. And so this is the case that we are wrong. Okay? So don't do this. So you don't need to do reduction. You should have a good laugh. Okay? So don't do that. Don't do that. You don't need to do that. But if you do, you say, okay, I just enjoy doing this, but you need to understand it can't be done, it cannot be done unless x minus 2 is guaranteed, which will lead you to the domain, which is the same. Okay, or another version, you say, okay, I'm going to do this, right? Because I just like to factor, right? And then if you write it this way, you can attach something like this, telling the reader that you can only do this if this is true. And then you also draw the same conclusion. Right? You draw the same conclusion, so the domain is still x not equals to 2. So you judge which version is most, it's the simplest. It's up to you. Okay, similar questions you'll find in number 5, right? And you find number 8. And and number 10. Okay, you find similar versions of how to determine domains, whether you simplify or not. Okay, they're all the same reason. And next, let's look at I will get to number 4. I will get to number 4 just a little bit. Okay, but I'm going to check out this absolute value situation. Okay, there's a number 9. Okay, and there's a number 14. So let's look at number 9 first. So f of x equals to absolute value of x plus 4 over 2x plus 8. At this point, I wish to bring to your attention about the properties of absolute value. Right here, okay? The properties of absolute value and how to work with absolute value. We have an introduction over here. These 2 sessions are extremely important, and we get to use them over and over again. In fact, these number 9 and number 14, these are your future, your near future homework questions. Of course, it's going to be in the limit setting. So please study these 2 sections. All right. Okay. So with that, in this number 9 case, you really don't have too much to worry, because the numerator absolute value domain is all real numbers. But all we have to do is set up 2x plus 8 not equals to 0. And you solve it. Okay, you get 2x equals to -8, and of course not equal, right? So logically, how you read it, right? If this is not equal to 0, then 2x is not equals to -8. And as a result, x is not equals to -4. And so our domain would be x is not equal to -4. You're done. Okay, let's look at number 14. Number 14, it's an interesting looking function, but you will encounter as we enter limit next week. Okay, so we have this very interesting looking function, right? As always, you just have to work with the original function. Don't try to find common denominators. You don't need to do that, right? Denominator cannot be 0. So the domain for this one is pretty straightforward. It's just x cannot be 0. You know that. Okay, so that's about absolute value related. Okay. Number 15. Number 15 looks a little bit more complicated, but it is still, similar. Okay, so x raised to the power 3 plus 2x squared minus 1 and 5 minus 3x. The numerator is polynomial. Denominator cannot be 0. So when you set up, all you have to do is just take the whole of the denominator and set it not equal to 0. And you solve it. Right? You solve it. You have 5 equals to 5 not equals to 3x. Right? Divide both sides by 3. So x is not equals to 5 over 3. All right. I think we're coming to an end before the number 4. Okay, I'm going to do number 4. How about number 12? To number 12 is straightforward, right? X cannot be 0. X cannot be 0. So let's get to number 4. Okay, so this one is h of x equals to, we have two things here, 4 minus x plus square root of x squared minus 1. So that's the function that we need to find its domain. Well, for this function to be meaningful, okay, for this rule to be meaningful, we have to recall that this function, this basic function, whoops, sorry, this basic function, which is the square root of x, its domain is x is greater than or equal to 0. Okay, so we have two roots. When we set up, we need to do 4 minus x is greater than or equal to 0. X squared minus 1 is greater than or equal to 0. How do we connect these two? These two must be connected. And the key word to connect them is and, because both must be meaningful in order to ensure the entire thing, the entire function is meaningful. So this keyword is absolutely important. If you are to work on these, and I'll be looking for this word in your work. Okay. Now, you're going to solve these inequalities separately. Okay. So on this part, we're going to get x is less than equals to 4. On the other part, we got something interesting. Okay, on the other part, we're going to solve this inequality, and we're going to get x squared greater than or equal to 1. How do we solve this latter inequality? Well, we take a square root, right? We take square root on both sides. We take square root. And the square root of 1 is, of course, is 1, right? So this piece is still 1. And the square root of x squared is absolute value of x. Absolute value of x. For this matter, I urge you guys to please, okay? If you have watched Solution to Entry quiz to calculus, okay, this is the very first question, which is illustrating the absolute value of x in relationship with the root of x squared. Okay, so that recording, the first question we covered is about why this is true. So we're using that. Okay, so the Solution to Entry Level quiz is nearly 2 hours long, but it covers so many common mistakes in calculus. Okay, in calculus. So I'm going to leave that for you. So from here, we get to here. What do we get? Next, the absolute value of x greater than equals to 1. This means x is going to be less than equals to -1, or x is greater than or equals to 1. So now what is the situation we have? We have come to this conclusion. Okay. But these two are together. These two are together. This is a more complex situation. We need to treat them as together. I'm going to put a curly bracket around these. Okay, so x is less than equal to 4 and the other one. And the and this OR case, what will turn this into? Okay, this is more like you have a, okay, and intersecting curly brackets. Let me grab curly brackets, B or C. Okay, this is a basic logic. And what does this equal to? This equals to A, your A and B, or, so these two will be together, or curly bracket B, A and C. Okay, so A and C. I know this is a little bit challenging. This is a logic, but that's how we solve this problem. This is how we solve this problem. So these two will turn into this piece and x less than equals to -1. So this is one piece. Okay. Or union is or x less than equals to 4 versus this is greater than equals to 1. So it turns into something like this. And then we need to find what is the common part. What is the common part? So for that piece, right? You want to find the common part of x less than equals 4 and x less than equals to -1. So what is that common part? Here we go. We got a number line. Okay, so here's -1 and here's +4. Okay, the common part means both conditions must be satisfied at the same time. Table. Okay, truth table, guys. Truth table has less than 20 minutes of lesson, but this truth table, understanding truth table, is absolutely essential for your success in mathematics. So less than equals to 4. What I'm going to do, I'm going to show you. Okay, less than equals to 4, meaning I'm going to put stars, right? Less than equals to 4. All of these are less than equals to 4, right? Till forever. And I'm also going to, for less than equals to -1, so that's all of these. Less than equals to 1. Anywhere that both symbols showed up, that's the result. So the end of this, okay, x less than equals to 4 and x less than equals to -1 is equals to, got it, x less than equals to -1 in curly bracket. Common part. Okay, so how about the second part? The second one. Okay, so let's look at number line. Let's look at number line one more time. Now, oops. Number line. Okay, we get a +1. We got a +1 and we got a +4. Okay, the part of our, that will be the result, is the part that must be marked twice. Okay, so we're gonna do the same thing again. Less than equals to 4, that's all of these. Less than equals to 4, that's all of these numbers. Greater than equals to +1, that's all of these. With which part it is being marked twice? Well, that part is being marked twice is, you've seen it, right? Is between 1 and 4. So x between 1 and 4. So now, finally, and we have this piece or that piece, right? Studying truth table, you know that if either one is, A or B is true, if one of them is true. So now, the final conclusion, so the domain is 2 pieces. One is x less than equals to -1, okay? And the other piece. So we have 2 slides of numbers. If you look at the domain, if you look at the number line, the part that's qualified for domain is here is 1, and here's the 4, right? So all of these are, I'm gonna put it as red. So all of these numbers are domains between 1 and 4, including 1 and 4, and less than -1, less than or equal to -1. So -1 here, okay? And all of these numbers, that's it. So our domain is 2 intervals, and these 2 intervals they're 2 disjoint intervals. I know this analysis is a little bit complicated, but I put it out there for you to challenge you. Okay, you'll be challenged from time to time, right? To understand the importance of the table at the basic level, also at a higher level. All right, for those of you who are on the STEM track, right, you're gonna get to discrete math in the future. And these kind of things you're gonna deal with very commonly in your future study. Okay, if you are into coding, engineering, and this logic is basic. So please spend time on this. And if you have any questions, please don't hesitate to reach out to me. And that's all for this lesson. Thank you for watching.